Everybody, give it up for Marc Messer.
Yeah, Marc.
Okay. Can everyone hear me okay? Sweet. Okay. I'll go ahead and get started then. So my name is Marc Messer. I'm local to Knoxville, so I'm super excited to speak to everybody here. I used to live like right up the road by Fulton, so that's how local I am actually. And yeah, reverse engineering is a really self-indulgent, tedious process, and I'm thrilled to have a room of people who want to listen to hear me talk about it for a bit. So I don't really have that much of an introduction for myself because kind of the less I talk about work, the more fun I can have talking about this. But I work in the defense space, primarily in incident response. It's fun. We get to see some novel malware, and it puts you in a situation where it's actually useful to have some reverse engineering skills on hand, where a lot of times that's sort of fiscally irresponsible, you might say. So yeah, we'll go ahead and get into it. And then I made a lot of art and illustrations for this. I've been working on this for a while, so I'm really excited to present here to you guys. So at a high level, what's reverse engineering? You know, forward engineering is what we normally do, where we have some kind of need for a thing. We go ahead and we write it, we make something, and then we have our output. And reverse engineering, we don't have all of that information typically. We may not have any source code. We may just have like a binary. You may just see network traffic. You may see whatever. You know, within this, I'm mostly going to be talking about just binaries and like Windows executables, but we'll get into all that. So if we have this binary and we don't have any source code, then how are we going to try and learn more about it? You know, there's the obvious thing of like running it and seeing what happens. If we suspect it's malware or something, that might be in a virtual machine or some sort of environment that's designed for us to, you know, see if it drops a file or opens up network connections, something like that. You also may do static analysis where you're really just looking at the object itself and seeing what you can sort of divin about its process or properties without even running it. So then what's the output? Like, why do we even do any of this? For a lot of stuff, it's because you want to write Yara. When I first got into it, it was because I was working. I was a teenager and I was interested in cheating in games because I'm terrible at them, but I still like winning. I don't do that as much anymore. But extracting intel, you might want to learn about your adversaries. You might want to, you might have a product that's EOL or something. And I don't know if that's legal or not necessarily, but you might need to learn more about it so that you can continue keeping it around if you absolutely have to. Learning to write better malware if you're interested in writing better malware. Going and looking at a lot of malware is a great way to go about that. DRM removal, software cracking, that kind of stuff. I should warn, I guess, at this point too, if you're like a really big evangelist of DRM software and like terms of service and stuff, then there's a really good talk across the way that will probably bother you a lot less. So then another thing of note for this is due to the tedium, it's sort of like CTFing if anyone played in any capture the flag events. You know, CTFs can be very frustrating because you might just get an image or something and you don't know if you're supposed to use that for OSINT. You don't know if it's like a layered PNG or something and you have to extract a flag from it. You know, you just have an image and you're told like, get me a flag. That can be just a really overwhelming process and really frustrating and you feel like you fail. And so I think there's a few things that you can do to try and make that a little bit easier. So taking what you know and using that to allow yourself to ask questions about what you don't know. A lot of times if we're working on an engagement or something, we call that like pivoting. Like we can say, okay, we notice this traffic, we're going to utilize that to see what else we can learn about what's going on. I would say too, and this is really helpful for software development as well, anything that seems initially complicated, you probably just have to break it into smaller, less complicated steps. Sort of like taking like a really complex algorithm or really difficult math problem or something like that. You know, how do you make it digestible and something that you can actually approach? And then failure is something that you just have to be super comfortable with. I would say I'm sort of like the Michael Jordan of failure in a lot of ways, in that you can always learn something out of that failure and just reapproach it and go again and see what you can do. Because most of the time, if you're just trying to figure out how something works, you know, you started out not knowing how it works, so it can't get any worse. That's maybe not a good mindset, but that's how I think about it. But anyhow, so to jump into this, we're going to go into a few technical terms, and really what I'm hoping to do here is say, hey, you know, there's all these sort of prerequisite topics that you need to be comfortable saying, I might not know everything about this, but how do I take enough information of what I do know to start approaching the environment in which a process or executable runs, the structure of that binary itself, and then understanding some of the instructions that are running to the point where we're essentially looking at a mechanical process at a certain point, right? When we get down to sort of the electrical engineering aspects of it. And we're not really gonna go too far into the weeds of that, but just know like we're gonna introduce a lot of concepts to show where they matter within the reverse engineering context. And it's okay to feel like you still don't understand a lot of stuff, because I feel like that every day, and reverse engineering is like my daily job. So here we're going to talk about forward engineering really quick. So we've got source code on the left. Hey, look at that. We've got source code on the left, right over here, and we're just doing like a really simple C hello world. And we know that eventually we have an executable, which if we looked at it in a hex editor, we would just see like hex output gibberish, right? For those of you who've looked at executables before, like you might immediately notice like, oh, this is a PE file, like a Windows DLL or a Windows EXE, something like that. And in between, we have the compiling process and we have linking. So this is important for us to note because a lot of times when people are trying to reverse engineer stuff, you're just going to look at like decompiling, something like that, which is a bit of a misnomer, right? Because you can't really decompile something per se. It's been compiled, but you are wanting to learn how you can understand that compiled output and maybe think of it in like a C-like fashion where we have sort of a pseudocode perhaps that looks like this, depending on your goals. So once something is compiled, say with like GCC or something like that, we have this compiled code output that starts to look a little bit more obtuse is maybe the way to say it. So we have some instructions that if you've never looked at assembly before, they probably look pretty foreign. And if you have looked at assembly before, they still probably look pretty foreign, and that's okay. We've got some instructions here that we'll talk a little bit about later, but right now just don't even sweat it. Although one thing to note is how many different instructions do we really see here? Like, I can't count that high, so I guess like 5 or 6, something like that, and we see them kind of repeated. So really there's not that much to memorize if you think about it. But so after we have that compiled output, we have something called linking, and linking is really important because a lot of times our code isn't necessarily just the code we wrote. For example, in this source code right here, we have printf hello world, and then we return to whatever. It's main, so I guess it exits the program. So that printf, for example, is not code that we wrote in there. We didn't specify how printf works. Like we didn't have to go write custom code to go and output something to the console, which is what that's doing. Somewhere in the machine, that is referenced and pulled in so that when we run this executable, it's executing this code that we did not use, that we symbolically reference with printf. So printf is therefore called a symbol. You'll hear me call that term out several times. And then the aspect of making that code accessible that we did not write is called linking. And so in this context, it's going to be talking about like external DLLs or something like that, that we're not reinventing the wheel. We're not writing our own custom thing. We're just printing that out. So hex code. Let's talk a little bit about hex code and why we're using it. Most of you may know this, some of you may not, but hex, we're just talking about something in base 16 that allows us to shorten things. So as we represent them in sort of binary methods. So looking at base 10, for example, the value 1000, we can see that takes 4 characters for us to represent. And then if we look at the value 1000 in binary, it takes a little bit more to represent. And unless you're just like a super genius, you're not going to look at that binary sequence and be like, oh, that's 1000, of course. Some people may be able to do that. I definitely am not. And then if you're really, really sharp, you might look at that hex 3E8 and immediately recognize that that's 1000. But why do we really have it represented that way? It's because it's just easier for us to shorten our representations of this information. It's also easier for us to read as bytes. If you combined down here, these two, these two, sections 45A and then 9000, that's a byte. So it's super easy to just represent everything that way and parse through it and understand what we're looking at. And what does it represent in this context? A lot of times it's opcodes. So if you think about the actual circuitry on a circuit, calling out specific things like moving something from one register to another is going to be like a literal opcode that's a capability of the chip. So B805, for example, in this, which I have over here on the right, would be moving to the EAX register the value 5. And the EAX register, think of that as like a variable space that's just baked onto the chip, like it's physically holding those bits. Data, we'll see some data in there as well, just strings of text, other values that you parse out from hex, that kind of thing. So a little code and getting us a bunch of output. Before we dive into more of the sort of fun stuff, one of the weird aspects that it took me a bit to understand is like why does something like print hello world spit out this like huge assortment of binary? Understanding that you have to have stuff linked in and make it run, that's still odd. So just note that like a lot of what you see in binaries is actually just meta information that is there so that the binary can be loaded in to the operating system, executed, and then you'll be running whatever you want. So that said, there's a bunch of headers that are in binaries. We're going to talk about that. That's an important aspect of looking at them. And then you'll have different sections within the binary that different parts of your code are going to be in there. So for example, in the hello world, we had the string of text hello world. That's not executing code. That's a data section. So there's going to be a section that literally just holds read-only data, and that would be going there. And the rest of your code would be in like a different section of the binary. The way I think of this is sort of an analogy to books, which I have on here, of course. If you pick up a book, you don't just like flip to the first page and then start reading it and wonder who this copyright character is and who the Library of Congress is. You're going to know like, oh, okay, I have to go to a table of contents. I'm going to go to whatever, and that's where I start. And the operating system essentially needs all that type of information too. You're also going to have meta information. In a book, you would have like appendices or something like that. Think of that like our data sections or relocation tables, stuff like that. That's all going to be an aspect of it. So let's talk about portable executable files specifically. So those are going to be Windows executables. So most of the time when you see something like that, you're going to think, oh, I have an exe. I want to play a Steam game or whatever. I run the exe that runs the program. You'll also see DLLs. They're actually PE files as well. And each of these follows a predictable structure because the operating system needs to be able to like pull that into memory and run it, obviously. So we will actually go and look at a binary in a minute, but that structure, we have something called the MZ header, which is there because Windows basically says, hey, if you try to run this on MS-DOS, we don't want it to just kill the system. We want this to just spit out a thing saying you can't run this on DOS and then move on. So there's actually a DOS program baked into the front of every single PE just in case you try to run it, because Windows is really, really dedicated to ensuring backwards compatibility for things that shouldn't exist. But I don't know. We're not going to go down that route. That's a whole talk. So then let's talk a little bit about sections that we're going to see when we look at these. So I've already mentioned a little bit about that, but so we'll see like a .text section. That's where our executable code is. We'll see a .data section. That's where our writable data typically is. Read-only data, R data, stuff like that. And really don't feel like you have to memorize all this stuff. I'm constantly referencing documentation all day. Like I have books on my desk. I have usually a window open with something, all sorts of stuff. So really, it all just kind of comes with familiarity. So let's look at an actual PE file headers. And here, I think this is actually, is this legible to people out there? Thumbs up, thumbs down? Okay, cool. Yeah, I wasn't sure what to expect. So that's a happy circumstance. But so if we look in here, you can see that we have some bytes that I've called out in certain different colors, right? And that's because if we're looking at just a raw hex dump of some of this information, then we can tell like, oh, this byte over here is referencing that this is a PE file, so that when Windows tries to load it, it's going to know how to treat that file. We'll see, let's go see down here. We can see the image base that the code is loaded into, and from there we calculate certain things called file offsets, in the sense that like we know that this is going to be mapped at some location into memory, and that if we take that location that it's mapped into, we can see something like the base of code, OX1000 right there, and we can know that 1,000 bytes or whatever that represents into the code. From whatever that base location is, we can see the beginning of our code. So some of this is saying, hey, from wherever this is loaded into memory, you count out this many bytes or what have you, and therefore you can find certain things. So I think we might even be able to see the address of the code entry point right here. And again, that's just a raw thing you can see in the hex dumps. So a good way of going into this kind of thing, really, to familiarize yourself is in some ways just opening something up in a hex editor, looking at it and seeing what you can figure out, which is coincidentally what we are about to do right now. So for this, I'm just going to pull up a hex editor. I'm trying to make all of this stuff concept focused and not really tool focused, because if you want to ask the right questions, that matters a lot more than which hex editor are you doing it in. It doesn't really matter. They display hex. You can go look at it. Cool. What else do you need? And then just referencing whatever you need to. So here we have a binary that's from Ophir Harpaz. I've linked to her Twitter later in here, but she wrote a site called begin.re that I think was pretty helpful. And she had some really nice binaries for beginning to get into analysis. So let's take a look at this. Let's say what we think it's maybe doing, and we'll see if we think that we could crack it. So here is something called O10 hex editor. OK, that doesn't really make much more space, but that's fine. So here we can see that we have certain header sections called out and just highlighted. So here, for instance, is that MZ header for in case this is loaded into a DOS machine. And then you can even see below that, this program cannot be run in DOS mode. And this is a full program. If you just cut it out and you run it in a DOS machine, it would work. And in fact, what's kind of funny is you can just change, because it's a hex editor and we can't edit this, we could just go change that text and have it say whatever we want. It wouldn't really do much for us, but that is a possibility. So let's go ahead and take a look and see what sections we have. So we see we have a text section. We have an R data section. So again, that's our read-only data section. We have a data section. We have resources, and we have relocations. So going through and looking in here, we can see our text is just going to be assembly opcodes. But let's go ahead and look at our read-only data and see what we can find. So in here, we've started to see string data that hopefully you guys can see from right here. But it's just asking us, hey, enter a password, and then it has this very suspicious leet speak, crack me, in there. Who knows what that's for? And then it either says correct or wrong password. So without knowing hardly anything about this binary, I think pretty much everyone in this room could just guess, hey, you enter in some kind of value, you compare it to some other value, and then you either get a yes or a no. And right now, I'm pretty sure if we were to just run this executable, which we can't because I'm on a Mac and it's an exe, we would be able to most likely solve this crack me. And a lot of things you look at, just going and identifying strings in the read-only section, if you just pull up your average run-of-the-mill ransomware sample, not to, I guess, endorse people doing that willy-nilly necessarily, but if you did and you just wanted to go and find the ransom note, you'll probably see it just in plain text, because whatever method they used to get it onto your system was probably how they worried about hiding it. As anything that goes and encrypts everything on your drive is kind of screaming alarm bells at that point. But anyhow, let's go ahead and jump back to the presentation. And we're making great time, by the way, y'all. This is fantastic. So please don't run for the doors, but we're going to talk about assembly for a little bit. And hopefully they've chained them by now so people can't escape. But we're going to talk about assembly for just a little bit, and it's not going to be nearly as bad as it might have been in college, or if you guys are weirdos and learn this for fun. We're basically going to talk about why this looks cool. I don't know if anyone remembers in school, in every math class ever, there are the people who are just oh, why do we have to learn this? How is this ever going to be useful? And it's usually algebra or something where you're why are you asking this? This is applicable to everything. But there's always people like that, and I wish that I would have had teachers who were hey, here's why this is interesting. Here's why we should care, because that's sort of part of the point of this. Is why should we ever care about assembly? Because you can do cool things with it. That's frankly the answer. And if you have like a violent hatred of dependencies, then you will love assembly because you aren't dependent on anything. So assembly, what is it? Opcodes, we're going to think of those as individual circuits on the CPU, just to foot stomp that again. You know, like a literal circuit path that is doing a thing, it's going to have an opcode. Syntax is usually kind of odd when you think about it before you realize about opcodes. So you'll have like the instruction name, like move a value, and then you'll have the destination it's supposed to go to, like a register such as EAX. And then you'll have your source operand, which is, let's say, the number 5, like we had on our first thing of, you know, moving the value to 5 to EAX. Why we say it that way is because move something to EAX register is a literal circuit. So it makes more sense to represent it that way. Certain disturbed individuals prefer AT&T syntax, which is essentially saying like the opposite, saying like, you know, move the value 5 into EAX. And that's fine, but don't ever do that. Nobody likes that. So registers, we're going to think of registers as values, variables again, that we've got just baked onto the chip, right? And there's stuff like microcode too, so like this all goes down huge rabbit holes, but I'm going for concepts more than I'm going for like hard accuracy. So those registers in 32-bit assembly, you have EAX, for example. We'll talk about what that's for, and it's 32 bits wide, holds a 32-bit value because we're talking about 32-bit assembly. And if you're using 32 bits of memory space and you pass it a 128-bit value, then in technical terms, everything gets broken. So we are going to just talk about things in 32-bit space. Some of these can be shortened into smaller registers. For example, if you were just using 16-bit, you would have AX. And if you just wanted to ensure that a value stayed in a 16-bit register, even in 32-bit assembly, you could pass it something like AX. We also have some indices and pointers. For the sake of time, we're just going to talk about the pointers. So ESP, for example, and EBP maintain our position on the stack. And everything on a computer that runs is essentially recursive. So you have, when you turn something on, like your computer or whatever, and you then open up a new process, that process was opened by something else. Like there's no island process that just doesn't have something that started it. So therefore, we're sort of just going to recursively call things through the stack and work our way back. And again, that's all nebulous. I've done a very confusing illustration, and we'll get to that sometime soon as well. So let's talk a little bit more about those registers and some of our flags and pointers, stuff like that. So EAX, think of this as, I just think of it as the accumulator register because of the A, frankly, just makes it easier. Stands for extended, that's the E in all of these. So we're often going to use that to store like return values after a function. The base register often holds function parameters, index addresses, that kind of thing. ECX, if you've ever written any code, you know, think of that as your counter. You might have a variable called I for iterations or whatever that you use all the time. EDX, you know, whatever, pass it data. And a lot of what I'm writing about function is really just dependent on how like compilers behave because they sort of have intended functions, but it's just a part of a machine and you can really use it for anything if you're just writing assembly. But there's also flags, and flags are really important because you aren't usually directly changing a flag or seeing a flag directly change, in my opinion. Like you don't necessarily see something like a 0 flag just like move the value 1 into 0 flag. You usually have something like a comparison that goes and changes these flags. So think about stuff like Boolean types, where you want to know if something is true or false, or you want to do like if or else. Like I want to do this, and if this is set this way, then I'm going to do something else instead. So if we have a function in assembly, function's the wrong term, but whatever, I'm already going. Like compare the EAX and EDX values, then if the EAX and EDX values are equal, then it's just going to stay as 0. So that way, if you have some kind of comparison later, then the 0 flag is checked. And if the 0 flag is one thing or the other, then it may do something like jump. So the next function here is just jump not equal, and that's essentially saying, okay, well, this wasn't set to this, just like an if-else function. Therefore, we're going to jump to this location in memory. So 40154B in this case, referencing a memory location. So there's a few different flags for checking to see if a result is negative, for example, or checking to see if you've overflowed a register or something like that. Then those flags get set for that purpose. So let's talk about the toughest part of this to learn. And really it comes with familiarity. It's going to seem confusing. It confused me for months, and I'm still going to be confused trying to explain it because it's pretty detailed. And really the best way that I found for just getting familiar with how the stacks work in assembly tends to just be I go to YouTube and I just watch people mechanically shift stuff around kind of like Towers of Hanoi until it's a little bit easier to understand. But so the stack is a last in, first out data structure. That is, in more friendly terms, think of it like a deck of cards. If you are putting something on top of the deck and someone else has to draw from the top of the deck because nobody draws from the bottom of the deck, then they're just going to pull the last thing you put in there. So it's always going to work like that. There's heaps, which are different. We're not even going to talk about heaps. But so at a high level, how does the stack work? We're going to push our variables onto the stack in reverse order if we need variables for a function that's being called. Something called EBP, the base pointer, is then pushed onto the stack next to help us tell where our function begins and know where we are in memory space, essentially. EBP is then assigned the value of ESP, which is the pointer to the top of the stack. So at this point, they're equivalent because we haven't really done anything with our function. And then as we move throughout the stack, say pushing or popping values onto it, then ESP is going to shift with it. And then after we're done with everything, EBP, that base pointer, is popped from the stack, and we return to the memory location where that function was called. And again, that's at a high level. Don't worry too much because we're going to look at it in detail. So in simple high-level terms, we save where we came from, and then we use our EBP and ESP registers to keep track of what we're doing, because you have to have some method for accounting in memory once you're working on things at a fairly low level. So let's go through this with an example, and we'll just talk about this code really quick. We are going to essentially start in this example that I run through where we call this subtract function. And the subtract function is just defined as taking two integers, creating a space to store an output, and then we are going to subtract one from the other and return that saved output. So pretty simple right there, and now let's make it really confusing by looking at it in assembly. So here we have the scene set for a function. You're going to notice right here, push EBP, move EBP, ESP. If you ever have to look at assembly and you just remember one thing from this talk, every single time you see that, a new function is being called, because that's setting the scene for a function to be called. So here I have a memory stack that I've written, and I just have this in 4-byte increments, sort of decreasing and increasing. So I like to think of the stack as counting down because I think it's easier to illustrate. If you watch videos of people doing like stack mechanics stuff, a lot of times they do it the other way. But whatever is easiest for you to understand, I think, is the way to do it. So let's go to where our function is calling. Again, that subtract function. And so we need to push those variables onto the stack, right? So we're pushing our variables onto the stack, and then they are showing up in the stack right here. We're pushing 5 for integer A. We're pushing 10 for integer B. And every single time we push, our EBP is rising a little bit. And so then we call subtract. So that pushes the return address of the function that called this, and then it jumps to the function address of the subtract function. So let's pretend we've just jumped over to there, and we're going to push EBP, move EBP, and ESP, setting up our pointers so that we can begin. So we have those variables onto the stack, and we pushed EBP and we moved EBP and ESP. So let's say that now we want to add some registers to hold integer A and to hold integer B. This is not necessarily a guaranteed 100%, again, copy of how a compiler works, but at a simple level, I think it's just an easy way to understand it. So we're saying, okay, we want some memory space to hold those values. So we're just going to push them onto the stack, and each time we do that, that's going to automatically move ESP because assembly is cool that way. So then, because we know, hypothetically when we wrote this function, that we're pushing it to values of a certain 32-bit space, we know that we can basically move these values at a predictable location from our function starting into EDX and ECX so that we have those values accounted for. So we've loaded those integers that we passed into EBP and EDX, or pardon me, into EDX and ECX over here. And so then we're saying, okay, well, I want to reserve some memory so that I can save what we're returning. So we're going to subtract 4 bytes from ESP, and that just allocates this empty memory space that we can therefore store a value in. So now we're going to perform that function. Again, to notice, I think I've called this out a couple times, but we're not actually, moving ESP for the most part on our own. We're not, every single time we push something onto the stack, we're not saying, oh, we need to move ESP so we don't lose count. The nice thing is that as a function of pushing and popping, ESP moves for us. But anyhow, so here we have our actual subtraction, and we want to subtract ECX from EDX. So that's our A minus B, and then we're storing that value in ECX. Because again, every value has to have a place to go. In assembly, you can't do something like subtract 5 from 10, because where are you going to store that value? Again, at this point, we're talking about like a mechanical device. So then we want to store that value to a location so that we can copy it to EAX and return with it. So that's what we're doing here. We're moving the ECX value into that integer C location where ESP is marking. And then we're saving that value into EAX, because after all of this is done and we pull all of this off, we want that value to be able to be referenced by the program. Otherwise, the entire function call was useless. So here we're going to clean up and return, and it's still probably going to feel somewhat confusing, and that's totally okay. So we're going to add 4 bytes to ESP. Again, this moves up and down here, so that's moving it back up. We're going to pop ECX. We don't need it anymore. We're going to pop EDX because we don't need that anymore. And then we are going to just use the instruction leave, which pops our base pointer. And then once we return to the address that ESP is pointing to, aka return address right here. And that would be us jumping back to main in that original example, and therefore having performed our function. Okay, so now we feel super confident about assembly. We've learned everything that you learn in a master's degree class or whatever. I'm sure that's basically all they cover. And we're just going to see if we can use that to take a look at that same executable that we looked at previously. And in here, we're going to go look at it in IDA-free. Yikes. Here, we're going to close IDA. And we are going to restart IDA. Excellent, and we're back. This is how technically proficient I am. That was effortless. Okay, so here we have some instructions. We can see those string values that we were looking at before. And so, again, we're probably just like, oh shit, we see like a bunch of different values that we don't know, what these do. I don't know what these instructions mean, whatever. So let's not panic really quick. Let's look at these instructions and we see, okay, we see move, XOR, push, load executable address, call. That's what, like 5 instructions. There's a test and a jump not 0 and an add. And so I'm not saying you'll never have to look anything up. But what I am saying is that like the amount of instructions that you need to actually like eventually learn and understand is not this like insurmountable amount. Like what looks like gibberish when you realize like, oh, I actually only need to pay attention to certain aspects of this to get some kind of information out of this that's actionable. It's really not that much. So we see here that the string enter password is pushed onto the stack, and then we see that a subroutine is called. So if we had to guess, knowing what we know now, that subroutine is probably what's printing that to the screen. So we know that if you're going to execute some kind of function, you have to push your variables beforehand. And then we see that happen again down here for crack me. We see crack me pushed onto the stack. We see the string that would have been entered as string 1 also pushed onto the stack. And so then we see a call for a string comparison. So there we know, okay, this is asking me for a password. This is telling me like, okay, I have this input, I want to compare it. And then after that, we jump based off of whether or not that worked. And so then we can see, okay, well, we jump either to correct or wrong password. And we don't even have to run this. We literally know, like, it's comparing whatever we input to crack me. And if it's not equal, then it goes to wrong password. So that's one function. And granted, things are a lot easier when you have like nice strings kind of telling you what's going on. But really, to start getting into looking at things like this, you don't need a bunch of fancy education. Like I literally don't have any reverse engineering training. I don't have a computer science degree. I think I still have a valid Security Plus, which I should probably check because I might need it for my job. But I do have a job too. That always shocks me. But anyhow, let's go back to our PowerPoint because we have 10 minutes and the cool stuff is just around the corner. So we're going to do a ROP chain because why are we doing any of this? Like, what's the point if we're just learning something about something? We're like, well, cool, this is how this works. See you later. You know, there's always a reason. It's never just this exercise that you're just doing for no reason. You always have some kind of output. So here we're going to talk about a ret to win binary, and the point of these is that you have a function that's like an island function. Maybe it's not referenced anywhere in the binary, and you want the program to jump to that function, even if running the function just as normal, it would never pop up. And that'll make a little bit more sense when we actually look at the assembly, and it will make sense because we're all confident and feeling great. So with some initial recon on this binary, let's just say that we found some function names like main, pwnme, and ret to win. And for this too, you'll see that I'm using GDB, which is the GNU debugger with pwn debugger installed and pwn tools and Python 2, because Python 3 is really annoying for exploit development. To put it bluntly, like it doesn't print to bytes natively and it's irritating. So yeah, let's go use some depreciated software that we're not supposed to use. And this is going to be an ELF file, which is a Linux executable. Why that's noteworthy is because it's going to be little endian. Endianness is something that we didn't really go into, but just think of the number on here. I have 31. We can say that this is little endian because the number 1 doesn't represent 10 like the 3 does. 3 represents 3 tens. That's bigger than the number 1, which represents 1, 1. So that's the smallest bit. However, if we were using a computer that had something like 13 being the equivalent to 31, where we were parsing it as like, okay, the first number is the least significant, meaning just the digit 1, and the next number means the most significant, which is the tens that we're summing, then we would say that that was big endian because the largest value number would be at the end there. But anyhow, so let's go ahead and look at our main function. Again, we see some stuff that's not super exciting. We just see a bunch of instructions that maybe we'd have to look up, and then we see that we call a function, we call another function, we call another function, and we jump to that pwnme function, and then we call another function. So these functions, by the way, we have something setting a buffer, puts at program linkage, is just outputting to the screen. It's like printf, think of it that way. And then we have pwnme. So let's go look at pwnme. In pwnme, if this was something that we didn't have to solve anything, it would eventually jump to that ret to win function, and we wouldn't have to worry about any of this. But we don't see that it jumps to ret to win at all. We actually just see that it sets some memory, outputs to the screen a handful of times, outputs to the screen again, reads some input, outputs to the screen, and returns to main. And so after it returns to main, then the function just ends. So let's look at that ret to win function. Again, we didn't find any references to this function. So if we just run that binary, this code is never going to run. So we see output to the screen. We see a system call here, so system at program link table, and then it just ends. So let's look at some GDB input. This is interesting because you can see your stack values as you step through a program. You can see the actual assembly that's being run, or pardon me, this is your stack values at the bottom, and you can see your registers at the top. So this is just us looking at the main function. Here, why do we see shell bin bash? Because again, everything is recursive on a computer. That's where we literally ran this from, was just from the shell. So that's why we see that. So we don't see anything interesting. Whatever, let's just continue running the program. So here we jump to pwnme. and again, we don't see that much. We can see the instruction pointer here, pulling our next instruction that we're going to jump to and run. We can see some stack values, whatever. We don't see anything that exciting. But if we continue running from there, then we see that it's going to prompt us for buffer or for input, and it says we're going to fit 56 bytes of user input into 32 bytes of stack buffer. What could go wrong? A lot of you here already probably know, but we're going to see if we can overflow that buffer. So here we're just putting in a non-repeating pattern that I just made with, I believe, Pwn tools. And then we just enter that when it asks us for input, and we see what we have. And here we have a program that crashed. So let's talk about specifically why that crashed, because that's why this matters. So we can see invalid address 616161, blah, blah, blah. So we also see that same value in EIP. So if we were a budding reverse engineer and we wanted to know, well, why did that crash the program, we would look into what EIP is and see that it's an instruction pointer. And then we would be like, oh, okay, this pointed to something that doesn't exist. There is no 6161C instruction. Like that's why it crashed. It reached to that for the next instructions that it can continue running, and that was just completely unavailable. So that being said, that's what we know. Let's create our exploit. So one of the important things from that is we know, like, okay, we put value that we wanted to put into EIP. So therefore, we can influence what that value will do. And so what happens if we just stuff the memory location for our ret to win function into the buffer overflow at the point where that value is read into EIP? So we see in our non-repeating pattern that LAAA occurs at the 44th character. So we know that that's where we want to input that, that value. And then we see, if we're looking at the ret to win function, it starts at 0804862C as the memory location. And so we just write a simple little buffer overflow exploit in here in Python, and we're printing 44 A's in a row, and then we're feeding it that memory location backwards because it's little endian. So we have 08, 04, 86, 2C, and then when we run that, we can see that we get our flag. And I wish I could do that live, but I think it would be too time intensive, unfortunately. But so there we've stuffed that input in, and then it goes to here, and then it crashes. And why does it crash? Because like the rest of the stack is just filled with garbage because we did a buffer overflow. If you really wanted to mess around with this, you could then figure out, okay, well, how do I make sure it doesn't crash when I do that? Like, how do I replicate what needs to be in there for this to actually return to main or something? That is the end of my presentation. So definitely thank you guys all for being here. If you want to learn more about this sort of thing, I would recommend following pretty much all of these folks, especially the top two. Both of these women have made incredible learning content. If you want to get samples, VX Underground is good. They do require a password, so I would message them on Twitter because there's sort of a meme that the password is infected, but really you have to go bug them. If you want to read some books about it, if you were going to get only one book off this list, POC or GTFO is fantastic. I have a blog that I guess I could have linked to on here. It's x86re.com. If you follow me on Twitter or add me on LinkedIn or something from the speakers page, then it's probably pretty easy to follow there. And a friend of mine does a lot of ASCII art, so I have them on here too. But yeah, I probably didn't leave enough time for questions or anything, but just holler at me. I'm not going anywhere. So yeah, thank you guys so much for listening to me talk about assembly.
Wow, that was an excellent talk. As somebody who did get a degree and took classes in reverse engineering, I will tell you that that 45-minute talk did cover several weeks of an entire semester-long course, so I'm a bit jealous. We do have time for probably like 1 or 2 questions. Does anybody have anything? Any hands? I do have a question. When at the start you said you were reverse engineering some games because you had some trouble, what games were you reverse engineering?
So really when I got my start in a lot of this stuff, it was in the context of like griefing with my friends because I was just an angry, dumb teenager. So a lot of that was like Day of Defeat, Team Fortress Original, Team Fortress 2, World of Warcraft. Really anything, like, it's sort of like antivirus in a way, anti-cheat. So like anything with VAC we felt pretty comfortable working on. Valve anti-cheat. World of Warcraft was mostly botting because I was like selling gold in college because I was just a freaking bum. But yeah, bunch of sweaty nerd games for sure.
Any questions? I don't see any hands, so I'm assuming there are no questions. All right, one more round of applause for Marc.